Welcome to lecture 15. Today's lecture is going to be an introduction to mechanism. So this is going to be an extremely important lecture. Most of the rest of the course, we will be looking at mechanism. So this is going to be considering the electron movement for chemical reactions. So this is going to be very important. Most of this course will be ionic reactions. I've written here, ionic reactions. You might also see polar reactions. Again, that's going to be most of the reactions in this course. And these reactions are reactions between a nucleophile and an electrophile. Okay, so what is a nucleophile? What is an electrophile? So a nucleophile is going to be something that's electron rich. It's going to be either a negative or a partial negative. Oftentimes it's going to be either a lone pair or a pi bond. Usually it's going to be a lone pair in this course, but we will see some cases where pi bonds, a different pair of electrons, could also be a nucleophile. So let's write some examples. An example could be an oxygen. So a lone pair on oxygen could be a nucleophile. It's electron rich, okay? It's a lone pair, and it could reach out to make another bond with something, okay? This lone pair could reach out and make another bond with something. We'll just put R. If it did, it would have a positive one formal charge. That's okay. But this lone pair could act as a nucleophile, okay? It's electron rich, it's a lone pair, it could potentially make another bond. Another good example would be an oxygen that's simply negative with 3 lone pairs. We could easily see one of these lone pairs here, I'll circle one pair, forming another bond with something, let's say a hydrogen this time, to make an alcohol, right? Electrophiles, on the other hand, are electron poor, electron deficient, and it's going to be a positive or a partial positive. So we could see, for example, a carbocation, a positive charge on a carbon, right? This is an electron poor carbon. A nucleophile, I'm just going to draw Nu as a generic nucleophile, could make a bond to that electron deficient carbon, which would give us this. Nucleophile bonded to that electron deficient carbon. Okay, so this is sort of the generic process for a nucleophile combining with an electrophile. Now, notice here this curved arrow. We talked a little bit about curved arrows. Curved arrows are showing the movement of electrons, right? The movement of a pair of electrons if we have this double-headed arrow on it. So the arrow is starting at the nucleophile because that's where the lone pair is. And we're showing that that lone pair is attacking that electrophile, that positive carbon, and making a bond to that empty p orbital. Okay, so we're showing the nucleophile attacking the electrophile, and this is going to be the general process for ionic reactions. Okay, the nucleophile attacking the electrophile. Okay, so that's the general overview of ionic reactions. I'm going to now break down the 4 different processes that we should know for drawing mechanisms. Before I do that, let me just show the generic, just a general mechanism for acid-base. We did see this before. If we recall from the acid-base lecture, we did a little bit of mechanistic work there. We would have a base that's negative, and we would have some sort of acid, and the acid would have a hydrogen on it. So this is just A for some acid connected to a hydrogen. Now, in an acid-base reaction, the base takes the hydrogen. So we have a nucleophilic reaction here, where this base is acting as a nucleophile, and this hydrogen is acting as an electrophile. Remember, the nucleophile attacks the electrophile. That's how we show the movement of electrons. These two electrons on the nucleophile attack that electron-poor hydrogen, okay? And when that happens, remember, these two electrons are left over on the acid, okay? The two electrons in the HA bond are left over, so the base comes and takes the hydrogen. It takes only the hydrogen, not the electrons that are bonded to it. Those two electrons get left behind, and we end up with the base now having the hydrogen, and we end up with the acid now having a negative charge. That acid now has a negative charge. Those two electrons are left over. We can color code those electrons. Let's make these red electrons part of the base. Now those red electrons are bonded to that hydrogen. And these blue electrons in this HA bond are now left over on A to give A minus. Okay, so the electrons are never changing from the base to the acid, okay? The only thing that's changing here is control of that hydrogen, control of that proton. So this is a nucleophilic attack of a base onto a proton, which is our electrophile. So this is one thing we've seen before. This is an acid-base reaction where a base grabs a hydrogen. This is similar to one of the four processes we'll discuss now. So the first process, the first mechanistic process we'll take a closer look at is nucleophilic attack, okay? Nucleophilic attack. So here are two reactions. Let's first look at the upper reaction. Here we have a bromine that has 4 lone pairs and it's negative. And then we have this carbocation. We have this positive charge on this carbon. So we have an empty orbital on that carbon. So if we consider this as a nucleophilic attack, what's going to happen here? The bromine with a negative, this is going to be our nucleophile. Okay, this is our nucleophile. And the positive carbon, the carbocation, this is our electrophile. That's our electrophile. So for a nucleophilic attack, we can show the nucleophile attacking the electrophile by drawing a curved arrow from one of the lone pairs. It doesn't matter which lone pair you select here, just any one of them. And we show that arrow going directly to that carbocation. We're forming a bond at that carbon that only has 6 electrons. It's a positively charged carbon. It has an empty orbital. So this lone pair from bromine is attacking that positive charge, attacking that empty orbital and making a bond to it. So if we have a nucleophilic attack of this nucleophile onto this electrophile, this negative charge directly to this positive charge, what would be the product? Well, the bromine is now bonded to this central carbon. So let's draw that over here. The bromine is now bonded to that central carbon. The bromine has 3 lone pairs, and that would be the final product. Remember, anytime you draw reactions like this, you should have a balance of charges. If you have a negative and a positive, then your product should be overall neutral, right? Or have a negative and a positive. Okay. So looking at the second one, so for the second one, we have an alcohol and we have a carbonyl. In this case, this would be a ketone. So what can happen here? So this is a new one. The upper one, maybe you could have done by understanding negative goes to positive, pretty intuitive. But for this one, we have to think a little bit more about what's going on here. One very important aspect of ketones, which you should get familiar with quickly is that ketones and most carbonyls have an imbalance of charge where the oxygen is partially negative and the carbon is partially positive. I'm going to highlight in red. This red carbon at the base of the carbonyl is partially positive. Partially positive. Okay. That pi bond is polarized, okay, to the oxygen. The oxygen is partially negative. The carbon is partially positive. So what actually happens here is that this oxygen could be a nucleophile over here because we have these lone pairs on these oxygens, and oxygen could go from 2 bonds to 3 bonds. So one of these lone pairs, doesn't matter which one, I'm just going to select this one here. This could be our nucleophile, and it could attack an electrophile. In this case, this partially positive carbonyl, okay? Now, it's not a full positive, it's not a carbocation like it was before, but you should be very familiar with the fact that carbonyls have a partially positive carbon at the base, and this is a very good electrophile, okay? So this can make bonds to nucleophiles very easily. So if we have a nucleophile like this oxygen, this nucleophile could attack this electrophile. Now, let's draw what that product might look like. It would be an oxygen with a hydrogen and a lone pair now bonded to that carbon, and then that carbon has a C double bond O, and something doesn't look right here. We have this carbon, the red carbon, has 5 bonds to it. That red carbon has 5 bonds to it. So that's not actually how we would draw it. So what we do in order to alleviate that issue, when this nucleophile comes in and attacks this carbonyl, the pi bond is kicked up to be a lone pair on the oxygen. Not the single bond, not the sigma bond, but the pi bond. The pi bond, remember from the resonance chapter, that pi bond is kicked up just like we do in resonance, kicked up to be a lone pair on oxygen, and that allows us to make a new bond, a new 4th bond to this red carbon. So again, this red carbon is right here. And that red carbon has 2 methyls on it. And then it has an oxygen now with 1, 2, 3 lone pairs. We have a negative, and this oxygen is now positive because it has 3 bonds. So we started overall neutral, and we end overall neutral, negative, positive. Again, that's a good check to make sure you did everything right. Okay, so this is going to be an extremely familiar process right here on the bottom when we have a nucleophile attack a carbonyl, and then the pi bond is kicked up to be a lone pair on the oxygen. Okay, so ingrain this one into your memory because we will see it very often in almost every chapter. Okay, nucleophile attacking the base of a carbonyl, and the carbonyl's pi bond being kicked up as a lone pair. Okay, so either way, these are 2 examples of nucleophilic attack. This is when a nucleophile, something that's electron rich with a lone pair typically, attacks something that is electron poor or electron deficient. In the top case, a carbocation. In the bottom case, the base of a carbonyl, a ketone. Okay? Nucleophile plus electrophile. So the second classification of mechanistic arrow that we'll be looking at is the loss of a leaving group. I'm probably going to abbreviate it quite often as LG, leaving group. So what happens in this type of mechanistic arrow? Well, we can have a molecule like this one shown here, this tertiary bromine. This tertiary bromine could undergo loss of a leaving group with this mechanistic arrow here. And it's very important to be precise with these mechanistic arrows as we draw them. This arrow should start on the bond. So I'm starting at the center of this bond, and I'm drawing this arrow right onto the bromine. Okay, let me draw these three other lone pairs here, because bromine has those lone pairs. And so what's happening here is the exact opposite of the nucleophilic attack. It's when this bromine is leaving instead of coming to make a bond and form this bond, it's leaving and breaking that bond. So this arrow here is indicating that these two electrons, let's color code this with red, these two electrons in that red bond are leaving with the bromine, and they're just leaving the molecule. So what would we end up with? We would end up with a carbocation at that position, because we've taken two electrons from that carbon, and bromine that's negative with 4 lone pairs. I'm going to color code here. We have that red lone pair right there. That's the one that was bonded to that carbon, but those two electrons left with the bromine. So now we have a carbocation and a bromide anion. Again, the charges should balance. We have overall neutral to start, overall neutral to end, positive and negative. So this is the loss of a leaving group. It's essentially the opposite of a nucleophilic attack. If we wanted to draw arrows going in the reverse direction, we would simply draw the exact opposite arrow. The lone pair attacking that carbocation would give us the starting material back. Okay? So this is the opposite of a nucleophilic attack. It's when a leaving group leaves. And we'll talk more about what constitutes a good leaving group in the future. But for now, we should simply understand these mechanistic arrows indicating that this is leaving, it's breaking that red bond right there. Now the exact same thing could happen down here with this water molecule, okay? This could leave by drawing that arrow there, just like the case above. Our leaving group leaves. We have overall positive here, so we should have overall positive in our products. If the water molecule leaves, let's color code this once again. Those red electrons in that bond are leaving. That means we have a carbocation here, positive charge. And it means we have H2O, water. We have a black lone pair, and then we have that red lone pair, which used to be a bond, but now it's a lone pair. So now we just have a free-floating water molecule with a carbocation. If we want to draw arrows going in the reverse direction once again, we're simply drawing a nucleophilic attack of water right onto that carbocation, and that's going to give us the product, the starting material back. Okay, so for loss of a leaving group, this is the arrow that we'll draw. You start in the center of that bond, and then you draw the arrow right onto the leaving group, whatever that leaving group may be. Again, we'll discuss that in the future. And what we're showing here is that those two electrons are leaving with the atom in question. So these two red electrons are simply breaking apart from the molecule and leaving. Okay, so when we have loss of a leaving group, we're typically going to be left with a carbocation. Okay, that's a very general trend. So the third mechanistic arrow we should be familiar with is proton transfer. And this is very similar to the acid-base arrows that we draw, okay? So sometimes we will see the reagents drawn directly over the arrows like this. In this case, we have hydronium H3O+, H3O+. So this is typically means you have some sort of acid dissolved in water, H3O+. So this is essentially acidic water. So what happens here? Well, we have this acid, okay? We have this hydrogen sticking out on this acid, and we have a lone pair, in this case on the carbonyl, the oxygen there. Now that lone pair could be essentially nucleophilic, and we could draw a nucleophilic attack where that lone pair grabs a hydrogen and leaves behind its electrons, just like we saw for the acid-base reactions. So again, the lone pair grabbing the hydrogen and the hydrogen leaving behind its electrons. What would that look like? So our product would be this oxygen now has a hydrogen bonded to it. It's now positive. And what's left over, we simply have H2O. Like that. So we started with a positive, H3O+, and we ended with a positive. So the proton is essentially transferring from one oxygen to the other. Now, could the reverse reaction occur? Of course, that's why we have reversible arrows here. The mechanism for the reverse reaction would simply be the exact opposite. A lone pair on the oxygen could take this hydrogen, and this hydrogen could leave behind its lone pairs on that oxygen, and that would give us back the starting materials. So proton transfers are almost always reversible. This proton could exist on this oxygen. This proton could exist on this oxygen. Doesn't matter. It could be either one. Okay. But the general process we should be very familiar with. It's when a lone pair takes a hydrogen, lone pair bonds to a hydrogen, and leaves behind its electrons. Okay, so the hydrogen is essentially transferring ownership. Let's highlight that red hydrogen. That red hydrogen could be on the water, or that red hydrogen could be on the carbonyl. Okay. Now, where that hydrogen spends most of its time, that's where we can consider the pKa's. Remember, higher pKa's means a more stable position for that hydrogen. Okay. But for this chapter, we're focused mostly on the mechanistic arrows. So this would be the mechanistic arrows for proton transfer. Okay. Lone pair grabbing a hydrogen, and that hydrogen leaving behind its electrons on the atom. So the fourth and final type of mechanistic arrow that we'll have to be familiar with is rearrangements. Okay. Rearrangements. So most of these rearrangements are going to be happening at carbocations. So we're going to discuss something very important, which is the stability of carbocations. Okay. So the most stable carbocation we can have is the tertiary carbocation, followed by a secondary carbocation, followed by a primary carbocation, followed by a simple methyl carbocation. Okay, so let me draw these out here. So a methyl carbocation would be just a carbon atom. So we'll put H3C with a plus. That would just be a single carbon with 3 hydrogens and a positive charge. A primary carbocation would be something like this. Just a straight, let me draw that a little more clearly. Just a single carbon with a positive charge. So this single carbon is connected to a CH3. And then this carbon on the end has 2 hydrogens, 1 carbon. So this would be a primary carbocation. A secondary carbocation would be something like this. It's connected to 2 other carbons. And a tertiary carbocation is the one we will see the most, which is connected to 3 other carbons. Okay, so when you see primary, secondary, or tertiary, that just means how many other carbons is it connected to. Okay, primary is connected to 1 other carbon, secondary is connected to 2 other carbons, and tertiary is connected to 3 other carbons. Okay. So why is a tertiary carbocation more stable? Well, it's something known as hyperconjugation. Hyperconjugation. We won't get too much into it this course, but we should be familiar with the term, and we should be familiar with the fact that hyperconjugation is simply a phenomena in which this positive charge, which is innately unstable, right? Positive charge on a carbon, it's unstable. It wants to be neutral. This unstable positive charge is stabilized by neighboring bonds, typically CH bonds. So when we have these CH bonds at neighboring positions, we get hyperconjugation, which is stability of that empty p orbital from neighboring CH bonds. Okay, that's as far as we'll go into hyperconjugation for this chapter. We may discuss it in the future, but we should be aware of the fact that hyperconjugation helps to stabilize those positive charges. So we prefer positive charges, these carbocations, to be at more substituted positions. So tertiary, sometimes secondary. It's very rare to see a methyl or a primary carbocation, okay, but we may see them. Typically, carbocations are going to be tertiary or secondary, okay? So when we discuss or when we see these carbocations in mechanisms, they are often going to undergo rearrangements. So this is going to be the 4th classification of arrow, these rearrangement arrows. So there's a lot of different rearrangements that can occur in chemistry. This chapter and this course, we will mostly just be focused on these basic ones, which happen around carbocations, okay? So what can happen around these carbocations that I've drawn here? Let's start with this one. We have the hydride shift. Now the hydride shift is going to occur when we have a secondary carbocation adjacent to a position where it could be a tertiary carbocation if only a hydrogen would move over. So a hydride shift is going to occur when we have a carbocation that could be further stabilized if a hydride shifts over one position. Okay, so I'm going to draw the arrow for this. I'm going to start in the middle of this CH bond, okay, and I'm going to draw an arrow directly to that carbocation. So this is called a hydride shift because this hydrogen in red, along with its electrons, both the hydrogen and its electrons, this whole thing in red is shifting over one position onto that carbocation. Now, why does that happen? Why does the molecule do that? Well, let's see what we get. If that hydride shifts over one position, now there's already one hydrogen here, right? There's already one hydrogen there in black. So now we have 2 there, one in red, one in black. That red hydrogen, that red hydride shifts over. And now we're left with a positive charge where it was, because that carbon that it used to be bonded to is now missing 2 electrons. So now this carbon is positive. So hopefully we can see from that shift, from that hydride shift, from this red hydrogen and its electrons moving over one position, we've changed this carbocation from a secondary carbocation to a tertiary carbocation. See how it's now tertiary? And that tertiary carbocation is much more stable than that secondary. So the molecule will spontaneously rearrange itself when given the opportunity in order to stabilize that carbocation, in order to give it a more stable position. So when a hydride shifts over, this is called a hydride shift. Sometimes you'll see it as a 1-2 hydride shift. And that simply means it's shifting over one position from 1 to 2. Okay, 1 to 2. If it's shifting over more carbons, it could be 1-3, 1-4, 1-5. We're not going to discuss those this course. All we're going to look at is this 1-2 hydride shift, where a hydride could jump over to the next carbon atom, could hop over, thereby shifting the position of the carbocation to where it came from to make it more stable. Okay? So the molecule is just rearranging itself to be more stable. So a methyl group can also do this. If we look down here, a methyl shift can also occur. You may, again, see it as a 1-2 methyl shift. 1-2 methyl shift. And this is simply when you have a secondary carbocation. This is the most common moiety that you'll see this on, is when you have a secondary carbocation adjacent to a position where it could be tertiary. Okay, could also happen in the case of a primary. Either way, the carbocation is being stabilized by this methyl group shifting over. So it's the exact same arrow above. Again, I'll draw it in red. This bond here, which is a CH3 connected to a carbon, I'll draw the CH3 there, CH3. This whole methyl group in red is shifting over one position. And when it does that, we end up not with a secondary carbocation, but with a tertiary carbocation. That red CH3 shifts over, and we go from a secondary to a tertiary carbocation, which is more stable. So the molecule will spontaneously do these rearrangements in order to better stabilize this positive charge. Okay? If that didn't make sense immediately, that's okay, because we will see some examples where we do these hydride or methyl shifts in order to stabilize that positive charge. Okay. Ultimately, what we should know from this slide, hyperconjugation stabilizes positive charges. We want tertiary carbocations. Secondary are the next most stable. Primary and methyl carbocations are very unstable. We will not be seeing much of those. But again, that tertiary carbocation is going to be the most stable, and that's the one that we want. Okay. We can undergo a hydride shift or a methyl shift on adjacent carbons in order to stabilize those carbocations. Okay, so let's work through our first full mechanism by going through this practice example. I've labeled each step of this mechanism with the type of arrow that we should draw, and I've shown the products. So all we have to do here is show the mechanistic arrows that are being described at each step. So let's start up here on the left, start where I draw this box here. That's our starting material. And we're going to work through this mechanism to describe the formation of the product on the bottom of the screen in the circle. Okay. Let's start with a proton transfer. If we take a quick peek at the product of this reaction, the box here, the product of a proton transfer, we're going to have an oxygen that now has an extra hydrogen on it, and this is a positively charged oxygen. So if we do a proton transfer with some sort of acid, we can grab the hydrogen from the acid, leave behind its electrons as a lone pair, and this would be a successful proton transfer where we now have this proton in red. Let's highlight it red here. This red proton has now been transferred onto our material here. We've protonated this alcohol. And so those would be the proper arrows for a proton transfer. Okay. Loss of a leaving group. Let's take a quick peek at our product from this reaction. It looks like the water molecule is leaving. The water molecule is acting as a leaving group, and it's departing from our molecule. Now remember, when we do this, we include the electrons with it. So we draw this arrow right here. I'm going to actually draw all my arrows in blue just so they stand out a little more. Here's the proton transfer arrows. And here's the loss of a leaving group. The leaving group leaves and it takes its electrons with it. So when this water molecule leaves, we're left behind with this positive charge. Now at this position, it says a rearrangement occurs. And if we peek down here at our product, it looks like a methyl group is shifting over one position to stabilize that carbocation. So let's draw a 1,2 methyl shift. A methyl group, now it's a methyl group because that's all we have here, right? We have 1, 2, 3 methyl groups attached to that carbon. If there was a hydride there, if there was a hydrogen attached to one of these carbons, we could do a hydride shift. But in this case, it's a methyl shift because that's all we have on this blue carbon. We only have 3 methyl groups. So surely one of them must shift over. Okay, so this would be a 1,2 methyl shift where a methyl group jumps over to that carbocation, shifting that carbocation to the tertiary position. So that would be the arrow we draw there. And then for nucleophilic attack, if we have Br minus and we have a plus, a carbocation, then the mechanistic arrow we would draw, starting from the bromine, starting from the nucleophile, attacking the electrophile, showing that we're making a bond from bromine to carbon, and that would give us our final product shown here in the circle. Okay, so this would be a combination of everything we've learned so far: proton transfer, loss of a leaving group, rearrangement, followed by nucleophilic attack. Now, obviously, at this point, I wouldn't expect you to do this mechanism just without any of the information here. What we're focused on is the arrows. Okay, the arrows are incredibly important. Eventually, you'll be able to do this mechanism blindly, just by giving a starting material and reagents. But for now, focus mostly on these arrows. Make sure your arrows are accurate. Make sure they make sense. Okay, I think we'll stop there for lecture 15. We'll get more practice on this in the next video, which will be the workshop. And obviously we will get much more practice since mechanistic arrows, drawing mechanisms, is going to be a major part for the rest of the course. Okay, so this is a very important lecture. If this one didn't make much sense, I would recommend rewatching it, studying it a little closer, because it will be very important for the rest of the course. Okay. Okay, see you in the workshop.